ready to stop plugging in forever and find out why it's not that simple. What wireless EV charging can do is impressive. What it can't do yet is the real story. Today we are peeling back the curtain on the wireless EV charging. I'm going to explain in plain language how it actually transfers power through the air, what eats up the energy along the way, and the engineering tricks people use to squeeze more juice out of the thin air. By the end, you'll know why some systems boast efficiency numbers that sounds almost magical, and why moving cars alignment mistakes and physics keep wireless from fully replacing plug-in chargers, at least for now. Why wireless charging looks like a magic. Picture this. You pull into a parking spot, step out, and your car starts charging without you touching a cable. That's wireless charging. Electricity jumps from a pad on the ground into a receiver under the car. It feels like magic because the energy crosses an air gap without a physical connection. The real trick is resonant inductive coupling. Two coils tuned to the same frequency like two radio antennas that prefer to talk to one another. When they're tuned and aligned, most of the energy goes from the one coil to the other instead of leaking into the world. Think of the system as three main parts: the ground side transmitter, the card side receiver, and the power electronics that convert between the car battery and the coil. The basics: the transmitter converts grid electricity into a high frequency alternating current and drives the coil to create an oscillating magnetic field. The magnetic field reaches into the space above the pad. The receiver coil on the car captures that magnetic flux and converts it back into the electricity. Power electronics then turn that into the DC current the battery needs. There are crucial engineering pieces. Resonant tuning. Both coils and their capacitors are tuned to resonate at the same frequency. Resonance boosts the energy transfer even when coupling is weak. Matching networks. These adapt impedance to keep system efficient across conditions. And we have ferrite shielding, placed behind coils to shape the magnetic field and reduce stray losses and interference. If those pieces are well designed and the car sits square over the pad, static wireless systems today can be nearly as efficient as wired chargers. Some industry and standards claim report efficiencies approaching the low 90s for well-aligned systems. What eats the energy? There are several places power gets lost. Understanding where they happen explains why wireless often trails wired charging. Resistive losses in the coils and conductors. Current flowing through copper or lead wire makes heat. Power electronic losses. Inverters and rectifiers are not 100% efficient. Switching devices and control electronics also waste energy. Also, there are magnetic leakage and stray fields, and not all the magnetic flux reaches the receiver. Some radiates into the environment and is wasted. There are some misalignment and air gap issues, and some of the efficiency falls rapidly if the coils are offset or the gap increases. Higher frequencies also can increase switching losses and generate more heat. A lot of research shows static systems commonly operate in the 80 to 93% efficiency window, depending on the design and conditions. But those numbers often exclude some supporting losses, like vehicle side inverter losses or thermal management requirements. The alignment problem. It's more than park poorly. If you park half a meter off, efficiency tanks. That's because coupling between coils depend on their relative position and the air gap. The amount of magnetic flux linking the two coils drops with distance and sideways shifts. Engineers have several answers, like coil geometry changes. Double D or DD coils and overlapping arrays tolerate misalignment better than simple circular coils. Larger coils and multiple smaller transmit coils in an array can cover a parking spot so the car always encounters a well-coupled region. Active tuning and power control. The system senses coupling and shift frequencies or impedance to maximize transfer. These are all the ways that engineers can improve the misalignment. Even with these tricks, moving vehicles, which cause variable gaps and constant misalignment, are a tougher problem. Studies on dynamic charging repeatedly show reduced efficiency versus static pads and added complexity for control and safety. Dynamic wireless charging. Power transfer while car drives over embedded coils. is a sci-fi version of wireless charging. The potential is huge: smaller batteries, longer range, and fewer stops. But the engineering challenges multiply. And we have some of these challenges like varying coupling as a car moves across multiple coils, timing and handoff between transmit coils to provide continuous power. There is a massive infrastructure cost. Buying coils in roads and powering them smartly needs so much money. Thermal management for coils and electronics under repeated varying loads is a hassle as well. Safety and electromagnetic compatibility when humans and other electronics are nearby is another safety risk. Simulations and pilot projects show dynamic systems are feasible but typically show lower transfer efficiencies and complex control needs. That's why most real-world deployments focus on static pads for parking or bus stops rather than full roadways. Standards, safety, and the numbers you'll hear. You'll see headline numbers like 93% efficient or only 1 to 2% less than wired. Here's how to read those. Standards such as SAE 2954 define performance classes and alignment criteria. Test results under the standard conditions, which can show efficiency up to low 90s for static systems. But those figures are for ideal alignment and include specific measurement boundaries. Independent tests and industry reports sometimes find that a well-designed static pad is only 1 to 2% less efficient than a similar wired charger, but that assumes ideal conditions and often excludes entire system-level losses. Peer-reviewed reviews and experiments often report a broader range, commonly 75 to 90%, depending on power level, coil design, and misalignment, especially when considering converter and inverter losses. Real-world installation with imperfect alignment and additional cooling often ends up in the lower end of that range. So the headline efficiency is the best case number. Real life, everyday efficiency depends on how people park, how well the system adapts, and what additional losses the manufacturer counts. The engineering trade-offs. Designing a wireless EV charger is an exercise in balance. Push one parameter and another suffers. Higher power also means more heating and stricter shielding. Without better cooling and stronger hardware, efficiency can drop. Higher frequency can also shrink coils but increase losses and EMI challenges. Bigger coils increase coupling and tolerance but heavier and costlier. And active tuning systems reclaim efficiency but add control complexity and failure modes. Engineers use these tactics to address trade-offs. They use multiple transmit coils in an array with intelligent switching to follow the vehicle across a patch. They employ DD or double D coils or rectangular coils to broaden these sweet spots for misalignments. They use SiC silicon carbide power electronics to reduce switching losses and improve converter efficiency. And they can add sophisticated communication between car and the pad to negotiate power levels and tune resonance. All of these add cost and complexity, which then feed into the big question: is the convenience worth the capex and the maintenance? A deeper look at coil design and resonance. Coil geometry and the resonance circuit determine how well energy transfers. Think of coil as a musical instrument. To make a loud note, both must be tuned to the same pitch. Resonance amplifies the magnetic coupling, so even if the coils are not strongly coupled geometrically, resonance helps move energy efficiently. Also, there are circular coils that are cheap and simple. Double D coils shape the magnetic field so that coupling holds up when the vehicle is slightly misaligned. And ferrite backing focuses the field toward the receiver and reduces stray fields. Wireless charging systems generate magnetic fields intentionally. Engineers must make sure these fields don't interfere with pacemakers, nearby electronics, or wireless networks. Standards set exposure limits and define test methods. Foreign object detection systems sense if metal like a coin or tool is on the pad and shut down to prevent heating. Shielding and intelligent power control keeps stray fields low for the bystanders and other electronics. Those safety features are necessary, but they add latency and control overhead. which slightly reduce practical efficiency compared to wired charging. Cities and companies have run pilots. Buses that charge at stops, taxis that charge overnight in special pads, and small scale dynamic trials. These pilots teach important lessons. Controlled environments are the easiest places to deploy. Maintenance and robustness matter as well. The outdoor pads must survive weather and debris, and fleet economics are often the first commercial win. Predictable routes and centralized maintenance make wireless attractive for buses and delivery fleets. Academic and industry reviews keep showing promise but also emphasize that wide consumer adoption needs cost reductions, better standardization, and more evidence of long term reliability. If you want to charge a truck at 150 kilowatts wirelessly while it drives, you bump into a mountain of problems. You need huge coils or many coils, powerful electronics, and serious cooling. The road needs renovation, power delivery upgrades, and control networks. If you lose 20% of energy in the road to the truck transfer, the lifetime cost and emission might be not worth it. That's why most attention right now remains on practical, smaller scale uses, parking pads, bus stops, and short dynamic trials, while engineers work on ways to make high power dynamic systems affordable and efficient. So, will wireless replace wired systems? Here's the honest answer. Wired charging is still the most efficient and cheapest per kilowatt hour delivered, especially at high power. But wireless is not miles behind anymore. For static, well-aligned systems, efficiencies in the low 90s are within reach. With smart coil design and modern power electronics, the deciding factor will be convenience, cost, and where the charging happens. For private garages and predictable fleet routes, wireless is already attractive. For fast public charging and high level power, wired system is still dominating. For the dream of charging on the move, the engineering is promising, but the practice still needs cost and efficiency breakthroughs. Wireless EV charging is a real, maturing technology that uses resonant inductive coupling to move power without a cable. It can be nearly as efficient as wired chargers when conditions are ideal thanks to resonance, advanced coil designs, and better electronics. But the technology faces limits. Alignment and air gaps are the biggest practical killers of efficiency. Dynamic charging introduces variability that lowers overall efficiency and raises infrastructure costs, and safety interferences and system level losses all nudge real world efficiency down from lab numbers. Engineers are attacking these problems with smarter coils, active tuning, semiconductor advances, and system level controls. The result? Wireless will likely grow faster in niche and fleet applications first, and then widen into everyday use as the cost comes down and standards mature.